Good day. I'm Mr. Valdez, and we're about to go through some truth tables and logic gates. Today, we're going to look at logical operators and how they're represented. We're going to combine logical operations to make expressions. We will create truth tables for logical expressions, and we will create circuit diagrams for logical expressions. So, first of all, before we start, let's just talk about what a logical value is. A logical value is either a value that's true or false. So if we have a logical or Boolean variable, that means that variable can hold one of these two values. For example, if we have a Boolean variable named isHappy, we could assign the value of true to isHappy. So we have three basic logical operators. We have the NOT operator, the AND operator, and then we have the OR operator. The NOT operator is used on one Boolean variable and gives one Boolean output. So your NOT operator inverts the value of a variable. So if we have a Boolean variable A, we have A being 0, which is false, and our output for not A would be 1, which is true. Or if the value of A is 1, which is true, the value of not A would be 0, which is false. This here is a truth table for the NOT operator. The NOT operator also is represented like this. So if we have not A, we can represent it like this. Not A, we can represent it like this. Not A, or we can represent it like this. Not A. So we have four different ways of representing the NOT operation. Second, we have the AND operator. And the AND operator joins two Boolean inputs and produces a single Boolean output. So the AND operator only produces an output of true when both inputs are true. So if we wanted to represent the joining of A and B, we can write A and B, or we can have A and B, or we can have A and B. All of these are different ways of representing the AND operation. So if we have A and B, we will have a combination. Both can be 0, A can be 1, B could be 0, A could be 0, B could be 1, or both can be 1. But the only time that our output will be true is when both values entered were true, or both values entered were 1. Next up, we have the OR operator. And just like the AND operator, it takes two Boolean inputs and it produces a single Boolean output. So the OR operator produces an output of true when at least one of the inputs are true. So all we need is for at least one input to be true for the expression to be true for the OR. We can represent the OR, A or B, A or B, A or, sorry, A or B. Right? So we have where the only instance that the output is going to be false is when both of these are false. Because once we have at least one value true, then the expression will be true. If both values are true, this condition where at least one value is true is satisfied. So now we move on to truth tables. We've already looked at truth tables for our basic gates. Now let's look at some truth tables for more complex expressions. If we have an expression A and not B, and we've represented this expression using our notation here, right, we can have A and B with both values being true, with one value, A value being true, the B value being true, or both values being false. Our output for such an expression would be this. How would we get to this? Well, first we would have to do the not B, and then we would have to join it with A. So if we had to go through this, we would figure out what not B is. Not B would have given us false, true, false, true. And then when we have the entire expression, we take the value of not B and we join it with the value of A. So false and true gives us false. True and true gives us true. False and false gives us false. False and true gives us false. So we have some exercises here where we want to create a truth table for the following expressions. So for us to be able to create our truth table, the first expression is not A and B. Let's create a truth table. We have A and we have B. Right? So if it is that we decide to do not A and B, first we have to find out every combination of A and B. So we have every possible combination of A and B. And then because we have to do this in order, we do it in the order of not, then and, then or. So we have not A being done. So we have not A, where we invert the values of A, and then we will have not A and B, right? And in this expression, we have not A and B giving us false, true, false, and false. Next up, we have not A or B. But what's important to note here is that we have a bracket around the A or B. So whereas in the previous one we would have had to do the not first, now the whole expression is subject to the control of the not. So we have to do A or B first and then invert the output from there. So if we have A and B, and we have the output for A and B being 0, 0, 0, 1, 1, 0, 1, 1. We will have to do A or B. And A or B will give us 0, 1, 1, 1. And then the output of not A or B will give us 1, 0. Next up, we have a longer expression, A and not B, or B and not A. And A and not B, or B and not A, will give us the following. First, we have to work out what not B is, and also what not A is. So we get 1, 0, 1, 0, 1, 1. 0. Then we can work out what A and not B is. So if we label this 1 and we label this 2, we could say A and the output of 1 is going to give us 0, 0, 1, 0. And if we take B and the output of 2, it's going to give us 0, 1, 0, 0. So if we label this column 3 and we label this column 4, then in column 5, we are going to get the entire expression, A and not B, which is column 3, or B and not A, which is column 4, and we will end up with 0, 1, 1, 0. So for the last expression, you notice that we have 3 variables. We have 3 variables, A, B, and C. Now, when we had 2 variables, we ended up with 4 different outputs, or 2 to the number of variable outputs that we had. We had A and B, so we had 2. So we had 2 to the power of 2 outputs, so it gave us 4 combinations. Now that we have 3 different outputs, 3 different inputs, A, B, and C, we have 2 to the power of 3 outputs, which should give us 8 different combinations. So let's see how these 8 combinations will go. We get A, B, and C. So we can get all zeros, we can get 1, 2, 3, 4, 5, 6, 7. And so if we were counting in binary, we would count from 0 to 7, and this will give us 8 unique outputs or combinations for A, B, and C. And so now our expression is A and not B, or C and A. So we will have C and A being done first because it's in bracket. So C and A will give us only an output of 1 when we have both columns as 1. So we get 0, 0, 0, 0, 0, 1, 0, 1. Next up, we have to do our knots. So after your bracket, you look for your knots. Where is our knot? We have a knot B. So we have a knot B, so we inverse the value of the B column. Sorry, 0, 0. And with that inversed value of the B column, now we have to do the ANDs. So if this is column 1 and this is column 2, our AND now is going to say A and not B. We've already done not B, so we have to do not B and A. So column 2 and A, which will give us column 3. Column 2 and A, so we will get, because this is an AND, both has to be 1 for the output to be 1. So this is 0, 0, 0, 0, 1, 1, 0, 0. And lastly, we're going to join all of this that we've already worked out with this section that we've already worked out. So using an OR. So we will get what was in column 3 or what was in column 1. And in this case, anytime we only have at least one 1, we give it a 1. So 0, 0, 0, 0, 1, 1, 0, 1. And this here is our truth table output. So we move forward to circuit diagrams. What are circuit diagrams? Circuit diagrams are logical expressions that can be represented diagrammatically as circuit diagrams. So to be able to create a circuit diagram, we combine the basic circuits to achieve the outputs desired. So if we had A and not B, our inputs would be A and B, and because we have to do not before the AND, we put the input of B into the NOT gate and take that output and feed it as the input for the AND gate along with A. Let's take a look at some exercises. So we have the same expressions that we had just now for, but instead of creating truth tables, we want to create circuit diagrams. So if we have not A and B, we're going to end up with two inputs, A and B. But because we have to do the NOT operation first, we invert the value of A and then join that to the B value. So this here is not A and B. Next up, we have a very similar expression, but note where the brackets are. So we want to invert the entire operation of A or B. So if we start with A and we have B, we can join these two using an OR gate, but then we have to invert the output of this entire operation to get not A or B. So we had A or B being done, but then we had to invert the entire expression. Next up, we have A and not B, or B and not A. So we really could only have starting points A and B. Let's take it one at a time because we have two sets of brackets. So we have A, and then we have B, but then we actually want the value of not B going inside of the bracket to join up with A. So this here gives us A and not B. We can branch off the value of B and place that into an AND gate. And then we also can take the value of A branched off and invert that and pass that into the AND gate as well. So this one down here gives us the value of B and not A. That's what this output is going to be. And then we take this output and we pass it into an OR gate to give us the expression A and not B, or B and not A. And lastly, we have three different inputs. We have the inputs for A, B, and C. We will do the C and A. So if we have A, we can branch A down to meet C, and they can join up into a gate. And so this output here is going to be C and A. And then the next thing that we would need is A and not B. So we can invert the value of B and join that up with A into an AND gate. And so this output here is now A and not B. We already did what was in the bracket C and A. And now we want to join these two up via an OR gate. And so this is our expression A and not B, or C and B. And that's the expression that we have. So, to round up everything, what did we learn? Today, we learned about logical operators. We learned about logic gates not and or. We learned about truth tables, which are ways of representing every possible output for combinations of values into a logical expression. And we learned how to display our values as circuit diagrams, our expressions as circuit diagrams. Thank you very much. I'm Mr. Valdez, and I'll see you in the next video.